we have the integral from negative a to a of the integral from negative square root of a squared minus y squared to positive square root of a squared minus y squared of the integral from negative square root of a squared minus x squared minus y squared to the positive square root of a squared minus x squared minus y squared. The integrand x squared z plus y squared z plus z cubed dz dx dy. We're asked to evaluate it by changing to spherical coordinates. If I ask you to focus on the outer two integrals and the outer two differentials, dx dy, where y goes from negative a to a, and x goes from negative square root of a squared minus y squared to square root of a squared minus y squared, do you know what shape that represents? I really wish I could get your feedback to see if you do. Folks, math is a language. What it means is there are symbols on a paper and it translates to a thought in your head. What I see here, y goes from negative a to a. Y takes on values that are both negative and positive. X takes on values that are both negative and positive because we're going from a negative square root to a positive square root. If we formed an equation using, say, an upper limit of integration, then x is equal to the square root of a squared minus y squared, which means, manipulating this equation a little bit, x squared plus y squared is equal to a squared. Folks, this represents a circle of radius a. If you already had that down, perfect, cool. Then it should make sense. It's not too much of a leap to consider all three sets of limits of integration and all three differentials to say this represents a sphere of radius a. How do you like that? I can translate all the math, but then I have trouble spelling the word sphere. For an entire sphere of radius a, theta goes from 0 to 2 pi to sweep all the way around the xy plane, because x and y are both negative and positive. Phi is going to go from 0 to pi, because we have the top half of the sphere and the bottom half of the sphere, and I know that because z takes on both negative and positive values because it goes from a negative square root to a positive square root. And then the interior of the sphere maxes out at a. Rho then maxes out at a and has a lower limit of 0 because there's nothing that tells me that there should be a gap in the middle of the sphere. Those give us the limits of integration. As far as the integrand, we have x squared plus y squared plus z squared. Folks, we can factor out a z. It shows up in every term. I have seen people take x equals rho cosine theta sine phi, y equals rho sine theta sine phi, and z equals rho cosine phi. I've seen them square all three of these, add them together, and then either successfully or not try to simplify the thing. Folks, what they've done is they've blown right past the fact that x squared plus y squared plus z squared is equal to rho squared. Go for the path of least resistance. Our iterated integral will then become the integral from 0 to pi of the integral from 0 to 2 pi of the integral from 0 to a of rho squared times z, but z is rho cosine phi, times dv, which is rho squared sine phi d rho d theta d phi. Since our integral has constant limits of integration, and we have a bunch of factors here as a product, we can split this up into three integrals. I'm going to try to be careful here. We have d phi is the outer one. That's the integral from 0 to pi. And we have a cosine of phi and a sine of phi in our integrand. So our first factor is, or our first integral is going to be from 0 to pi of the cosine of phi times the sine of phi d phi. Next we have d theta. That goes from 0 to 2 pi, and I don't see any thetas in the integral, so 0 to 2 pi d theta. You know, I said next we have d theta. This doesn't have to go in any particular order. It's a product, right? Just wanted to make sure that was clear. And finally, we have d rho. Rho goes from 0 to a, and it looks like we have rho squared times rho squared. It's going to give us the integral from 0 to a of rho to the 5th d rho. For the integral with respect to phi, if I think of the sine of phi as u, then the du is cosine of phi d phi. And so that integral turns out to be 1/2 times the sine squared of phi. That'll be evaluated from 0 to pi. If you already know what's going to happen because of that, then you're cool, you're good. Otherwise, let's just keep going here, folks. D theta is going to go from 0 to 2 pi, so that's going to give us a factor of 2 pi. And then integrating rho to the 5th d rho is going to give me 1/6 rho to the 6th evaluated from 0 to a. Now, folks, what we have in the 2 pi and the rho business is some finite number, right? But from the first factor, I have sine squared of phi. It's going from 0 to pi. If I put either pi or 0 into phi, I get an answer of 0. The whole first factor zeroes out. The whole integral turns out to be 0. That looks like just a donut, so I'm going to put this one in a box. That doesn't look much better. Anyway, we can see how this makes sense because our integrand was odd with respect to z. And we have a completely symmetric region. And so the fact that this integral turns out to be 0 shouldn't be much of a surprise, although maybe a little bit of a disappointment.